Next up on the agenda, our last presentation of the day, Robert Bocchino of NASA JPL giving a demo on the FPP ref application model in F prime 3.0. So Robert, this is giving a demonstration. So Robert, I think the screen and the floor is all yours.
Thank you very much. Can you hear me?
We can hear you just fine.
Great. Okay, I'm going to share my applications here. Can you see the slides?
We can.
Okay, thank you. So as Brandon said, I'm going to present on the FPP ref application model in F prime 3.0. So this is a demo. So the way it'll be structured is I have a few slides to go through to give some context, and then I'll get to the demo part. So by way of context, so this is in the context of the F prime Flight Software framework, which is a flight software and embedded systems framework developed at JPL. It's free and open source. It comprises several elements. So it provides a modular architecture based on components and ports, a C++ framework that gives basic capabilities such as threads and queues, several tools for specifying high-level models of flight software and generating C++ code, a collection of components that are well-defined and ready to go and unit tested, so you can just plug them right into your flight software applications, and tools for unit and integration testing. And it runs on a variety of platforms, including desktop and embedded, and it's available at the link shown on github.com. In terms of the architecture, so the key concepts in the F prime architecture are component, port, and topology. So a component is a unit of flight software function. In the F prime implementation, it's implemented as a C++ class. So you can think of it as like a class. There's one definition, you can have multiple instances of it. A port is a point of connection between component instances, and a topology is a directed graph of instances and their connections. So basically, a flight software application is described by a topology. Importantly, component instances are going to communicate only through ports, so there's no global shared data, and also there's no compile time dependencies between components. So basically, nothing in the component implementation depends on how the components are connected. So the implementation and the connection are separate, and that makes the system modular. The port connections are typed and statically specified and checked, and they can be either synchronous or asynchronous. So synchronous means that when you invoke a port, some work is done immediately, and asynchronous means that when you invoke a port, a message goes on a queue to be dispatched on another thread. Okay, and the basic idea here is that the architecture is going to provide structure. It's going to enable automatic checking of correctness properties, for example, that the types of the port connections match properly. And also, the modularity is going to enhance the reusability of the flight software components. Okay, so now moving on to F prime modeling. So the idea is we have these components as shown schematically with the ports and connections. And so the F prime developers are going to write some models, and then the F prime tools are going to generate code from the models. So the models include definitions of components and ports, connections specified in the topology, and also the elements of the flight ground interface, such as command and telemetry definitions. And then the F prime tools will take the model and will generate C++ component base classes that are implemented by deriving from those classes, and C++ code for setting up topologies and XML command and telemetry dictionaries. Okay, so that brings us to FPP, or F prime prime. So FPP is a new domain-specific modeling language for F prime. So it allows you to describe the models that I just described in the previous slide. So it's also free and open source like F prime, and it's simple and easy to use. And it provides several advantages when doing F prime modeling. So it provides a succinct and readable source representation, a robust error checking reporting. There's good integration between the model and the generated code, and there's also an accompanying tool for visualizing topology graphs. And as of F prime 3.0, which was released in late December, it's integrated with F prime. So you can now use FPP to write the F prime models and do the code generation. And it's also available on github.com at the link shown. Okay, so in the rest of the talk, I'd like to talk about the F prime ref application. So F prime comes with a ref, short for reference application. The idea is to provide an example that is, somewhat unrealistically small, but still illustrates all the main features of F prime modeling and code generation, and provides an example of a runnable deployment illustrating commanding and telemetry, and it's controllable through the F prime ground data system, or GDS, which is one of the tools I mentioned. So F prime comes with a simple lightweight tool for doing command and telemetry. So before F prime v30, the ref model was handwritten in XML. And as you can imagine, it was, because of the nature of XML, the modeling was a little bit verbose and tedious. So we think that doing it in FPP makes it better. And so for F prime 30, we translated the ref model to FPP. And so to do that, we used a tool called FPP from XML, which is a mostly automatic translation from XML to FPP. There's still a little bit of hand tuning that's required, but it does about at least 90% of the work for you. And as mentioned, it translates the F prime XML model elements to FPP, element by element. Okay, so now I'd like to get into the demo part. So in the first part of the demo, I'll show you the FPP ref model. And there are 4 elements that I like to show. So the first element is the types and ports, and then the second element is components, and then component instances, and then the ref topology. So to do this, I'm going to switch over to my terminal. So can you see the terminal okay?
Yep, we can.
Okay, great. So I'm now in a working copy of the F prime repo on the GitHub. I'm in the devel branch, which is, I guess, slightly ahead of the v30 branch. So the first thing I would like to show you here is the types and ports. So for that, I'm going to go into the FW command directory. So FW command is part of the framework, and it defines framework elements relating to commands. So in here, you can see that we have if you do an ls, you can see there are several files. So one of them ends in .fpp, so that's the FPP model file. So in this directory, all of the FPP model elements are described in this one file. And if you open it up, you see it's wrapped in a module FW, that's for framework. And there are several elements here. So one of them is a type. So this is what's called an abstract type, or in FPP. So the idea is you can name a type in FPP that's opaque to the model, but it's implemented in C++. And then you can use the type in the model. There's also a port definition for command registration, a port definition for sending commands, an enumeration type representing a command response, and a port for sending command responses. And so each of these ports is defined very much like a function call. The idea is that there are formal parameters that are typed, and the formal parameters specify the types of the data carried on the port when the port is invoked. So that's a sort of very brief overview of types and ports. So next we can go to components. So to do that, I would like to move over to the SVC directory. So SVC stands for service. So that's the service layer in the F prime core repository. So it contains components and helper elements for the service layer. So in particular here, we have something called the command dispatcher. So SVC command dispatcher, and that's a component for dispatching commands. So I'd just like to show that model. So here we're in a module called SVC. So a module in FPP is kind of like a namespace in C++. So it just qualifies all the names so the names don't clash. So here we're in the SVC module, and we're defining an active component called command dispatcher. So in F prime, an active component means a component that has an associated thread. So that there's a dispatch loop that can block on a queue and wake up when there's something to do. So that's how we implement the asynchronous dispatch that I was talking about before. And here you can see there are several port definitions. So here are the ports that I mentioned. So we group them into what's called general ports. So these are user-defined ports that have a name and a type. And you can see that some of them are arrays. So arrays are allowed. So we can have arrays of ports. And some of them are input, some of them are output. And then for input, there's synchronous and asynchronous. There's also something called guarded, which is guarded by a lock. So this is just to kind of give an overview or a flavor. I don't have time to go into all the details, but you kind of get a sense of what the port definitions look like. Then we also have these port matching specifiers. So the command dispatcher is a little bit special because it has a pattern where registrations come in on each on its own port. And then when command dispatches go out, they have to go out on the matching port. So we specify and check that property here with a matching specifier, saying that there are pairs of ports where the assigned port numbers in the topology have to match properly. Then we have these special ports. So these are ports that have a special syntax and a special meaning in F prime. So they include ports for commanding, for issuing events, so events are a special kind of telemetry that just report an event, like something happened. And there are also ports for telemetry and for getting the time. Okay, and then this is the flight ground interface I was mentioning. So in F prime, the flight ground interface is specified component by component. So each component can specify its piece of the command dictionary and the telemetry dictionary and so forth. So here we have some command definitions. Each command has a name, an opcode, and some arguments. There are also event definitions. So these are arguments that are bound when the event is issued. And the result of issuing an event is to send a message to the ground, and the message is specified here as a string with some format specifiers in it. And the format specifiers get bound to the arguments when the event is sent. So we have a bunch of events here, and then we also have telemetry. And so these are telemetry channels, which define a pair, each channel defining a pair of an ID and a type. And then so when the flight software is running, it can send out telemetry points, which are specific values with that ID and type. Okay, so that gives an overview of a component. So now I'd like to switch over to the topology. So now I'm going to go into the ref directories. That's that ref example I was mentioning. And within the ref directory, we have a directory called top for topology. And now in here, you can see there are two FPP files. So there's one for defining component instances and one for defining the topology connections. So first, I'd like to show you the component instances. So remember, as I mentioned, an F prime component is like a C++ class. So there's going to be a definition. So the component definition I showed you is kind of like the class definition. And now we're going to have instances of the component. And that's kind of like in C++ declaring a variable with that class type and getting an instance of that class. So here are these sort of the equivalent of the variable declarations in FPP. That's what they look like. We can go to the CMD disp instance. So this is the one instance of the command dispatcher that we have in the ref topology. So you can see that one's pretty simple. It just gives a name, CMD disp, a type, SVC command dispatcher. There's a base ID, which provides a base number where all the opcodes and telemetry IDs for this instance will start to differentiate the different instances. And then there are some particulars like a queue size and a stack size and a priority. And we have those because this is an active component. So it has a queue and it has a thread. So we specify the attributes there. And then if you browse through, you can see that some of these other instances are a little more complicated. Like here's file downlink and it has some more stuff in it. So basically this other stuff consists of C++ code snippets that get inserted into the setup and teardown code. So basically what happens is in F prime, when you instantiate a component, there's often some little bit of C++ that's required, like specifying the timeout or configuring the component and so forth. So instead of trying to redefine all that in FPP, we just let C++ handle it. So we allow the user to inject snippets of C++ code into the model and specify the phase of initialization or termination at which the injection should occur. Okay, and then I'd like to show now the topology, FPP. So here we have a topology file that defines the ref topology with several instances. So here we're repeating the instance names, and that's because we want to be very particular about which instances are used in this topology. So in general, we can have multiple topologies and topologies can import each other. So the idea is we define instances in one place and then we use them in another place. This place specifies all the uses. Then we have pattern graph specifiers. So these specify patterns of connections that would be tedious to write out by hand. So for example, the single line command connections instance CMD disp in line 61 says that CMD disp is a command dispatcher instance. And then FPP knows what that means, and it knows how to hook up all the command registration and command responses and so forth. So you don't have to write out all those arrows yourself. But then some arrows we do have to write out ourselves, and they're written here. And so you can see that they're grouped into named connection groups. So for example, there's one for downlink, one for fault protection, one for rate groups, et cetera. And each connection specifies an output port, an arrow, and an input port. Optionally, you can specify an array index as shown in line 104. In most cases, you don't have to. Oftentimes, it's 0 or it can be numbered automatically. and you don't really have to worry about it. But something, you know, if you want to specify it, if you need to, you put in a number. Okay, so that's what the connections look like. So now I'd like to shift over and talk about the tools, the FPP and F prime tools. So there are 5 elements here. So translating XML to FPP, checking FPP models for correctness, generating code, visualizing topologies, and finally compiling and running the ref application. So first, for translating XML to FPP, what I'd like to do is, so I've got everything already built here, and this is using CMake. So F prime uses CMake. So there's something called a build cache in CMake. And so I'm going into that build cache to where all the generated code lives. And actually, wait, let me back out of here. So now I'm going to the build cache version of that FW command directory that I showed before. And you can see that, aha, I wonder if maybe this isn't quite built. Hold on. I think I have a version of it built over here. I'll go over here. Okay. Okay, for some reason, I'm not finding the XML. Okay, so I guess I'm going to move on for now. I was going to show how to translate the XML, but for some reason, I just can't find the XML file. So for checking FPP, let's go on to checking FPP models for correctness. So for that one, I'm going, oh, I know why. It's because I was in the wrong build cache, right? So I need to be in the build cache for ref. Okay, I was in the main build cache. So this one should work, right? Okay, so now I'm in the ref build cache, and you can see the XML files there. So what I wanted to show here is I can run FPP from XML, and I can just run it on all the AI.xml files. So those AI.xml files are generated from the FPP. And actually, I can show you one just to see what it looks like. So this kind of stuff is what's generated from the FPP. And then you can convert this back to FPP by running the FPP from XML tool. So you can run it on those XML files and then dump it into this command dispatcher FPP. And so essentially I'm reconstructing what I showed you before that was written actually, you know, using this translation, but the other one was tidied up a little. So it doesn't look quite as, you know, the auto-generated one doesn't look quite as nice, but you can see it's close. So this shows you how you can port from legacy F prime XML to FPP. Okay, so moving on, let's go to checking FPP models for correctness. So for that one, you get out of the build cache and go to the top directory. And let's see, for that one, so I can run this command. So F prime util is the build utility for F prime, and I can run FPP check and then give it the options -u unconnected.txt. So what that will do is it will check the ref topology model that I showed you before. So it didn't report any errors. That means that the semantic check worked. And I also asked it to put all the unconnected ports into a file called unconnected.txt. And so that there's the output. And so this is showing you all of the ports that are defined but not connected in the topology. And that's useful to review and make sure that, you know, check whether any of these should be connected. Okay, so now I'm going to, I think I'll skip, I think in the interest of time, I'll skip the generating code part. I want to just go to visualizing topologies. So to do that, I will run, there's a tool called FPV for F prime visualizer. And then you run that and it sets up a little server, and then hopefully you'll be able to see Safari here. And if I put this in, okay, wait, that didn't work. Hold on one second. Oh, I know why. Sorry, because I'm in the wrong. Sorry, just I have multiple versions of F prime going here, so I have to make sure I'm in the right one. Okay, so do that, and then it should work. Okay. Let's try that. Okay, there it is. So this is showing you the command topology for that ref application. And then there's a menu and you can go to the different, so these are the subtopologies. So each of these subtopologies corresponds to one of those connection graphs I showed you. And the command one is actually one of those auto-generated ones. So this is a helpful way to see what's actually there. So remember when I showed you the topology file, there was just that one liner that said put in all the command connections. And when you pull up this version, you can actually see all the connections that are there. And then there's one for rate groups. This shows how the rate groups are connected and so forth. Okay. So I think at this point, I'll pause and see if there are any questions.
All right. Thank you so much, Robert. We do have about 5 minutes or so for some questions. I got one here from Jack White in F prime 2.1. It is difficult to declare new types inside a component, and it is better to do it in a discrete enum or a serializable XML file. This is even true of arrays. Is it now possible to fully specify enums, structures, and arrays inside a component or port spec? Can you declare command arguments and arrays? Yeah.
Okay, good question. So the answer is mostly yes. So FPP allows this. So FPP allows you within a component definition to define a type, including an enum, an array, or struct type or abstract type. So that's certainly allowed. The caveat is that the way it's co-generated right now is a little bit not ideal. And it's basically because we're interfacing with the legacy autocoder. So what we would like eventually is for the code generation to generate that inner structure as an inner member of the component class, right? Because the component, let's say you have a component C and you define a type inside it, we would like in C++ for that type to actually be a member of the class C. So it's currently not that way. So in C++, it's outside, but it's qualified with, the name is qualified with the component name. So, it's close.
Okay. Next question from Eddie Benowitz. What version of the C++ standard do you target?
Right now we're targeting C++ 11.
Okay.
And yeah, and we thought about C++ 14 because I guess C++ 14 fixes some bugs in C++ 11, but it seems like it's not fully supported in all platforms. It's always tricky, but 11 is what we currently use.
Okay. Next question. Is it possible to generate the FPP files from the F prime 2.1 XML?
Yes, so that's part of what I showed, right? So that the part where I showed going into the generated code and generating FPP, I used the generated code in F prime 3.0 because all of the source code is FPP, but in F prime 2.x, the source code that's actually checked into the repo is XML, and you just do the same process that I showed.
Okay. Next question. Can IDs be specified absolutely instead of an offset to a base ID? And can you merge channel and event IDs into one shared pool? Okay, so I think the answer to both of those questions is no. So for the first question, you pretty much have to specify relative IDs and then the base ID. And the reason for that is so that you can instantiate the components and also so that you can check at instantiation time that everything is in sync. So that's currently the way we have it. And then as far as the merging into a shared pool, so you could, I think you could do something like that using constants. So FPP allows you to define constants. So if you wanted to, you could define constants for your IDs and then kind of share the constants among the events and telemetry. And yeah. And now, as far as the first question, I'm not entirely sure. Maybe I have to go try it because it depends on how the checker works. Like the checker is definitely going to check that nothing collides after resolution, but whether it, I don't know. I have to try. Okay.
Yeah.
All right. Next question from Peter Fiddleman. If you wanted to change the topology at runtime, such as connecting components in a different way, is this possible, or would you need to compile and load a whole new binary?
Right. So currently the connections are statically specified, right? So in the F prime topology, it's compiled in.
Okay. And next question, how would someone new to aerospace decide whether to use CFS or F prime or RTEMS in their system?
Right. Good question. So there are different trade-offs, right? So I think, I mean, I think you just have to kind of look at the different attributes and then figure out, where you are in the trade space. But so, I mean, one difference between CFS and F prime is C versus C++. There are also architectural differences. CFS uses a software bus, and F prime uses connections specified in the topology. And there are other differences. I think you just have to look at all the differences and see which one's the best fit.
Yep. And I'll note for anybody interested in the answer to that question, we will also have our frameworks town hall on Thursday with representation from both the F prime and CFS teams. So that would also be a good time to ask that question again. Last question that we have time for, is there a way to generate code from a visual topology like Magic Draw?
Okay, so we had a version of that, and then we kind of deprecated it because the way it was implemented was kind of unwieldy. So we're thinking of trying to resurrect something like that. So currently we don't have that, at least in our production version, but we're thinking about it, about how to bring it back.
Okay. And that's all we have time for. Robert, thank you so much for your time this afternoon.
Thank you.
All right.